Okay, so I just start the record and we will move forward. I will first present myself. So I'm Pelagie Alves. I'm working as a dissemination and communication leader on the EUPEX project. And I'm hosting webinar for this project. So today's webinar will be manual and automated optimization techniques for the integrated forecasting system, and it will be presented by IFS. Before moving to the main topic of today, I first want to introduce this webinar series. So the EUPEX researchers are sharing their results and lessons learned. That's why we are organizing monthly webinar to showcase application and also tools in the within the EUPEX project. The goal is to connect experts and share experience. So we have also a webinar planned for October. It will be Big TFT by CEA. And in November, it will be SpecFrame 3D by Chinica. You can find everything on our website and the program, and you can register. Okay, and now today's topic. We will talk about IFS and NEMO. And our speakers will be Andrew Beggs and Lale Pouyan from ECMWF. Lale and Andrew work as computational scientists in the computing department at ECMWF. So first Lale, she's from Ireland and moved to Germany to pursue a PhD in HPC. She works at ECMWF since 2022. Our research work mainly involves profiling, benchmarking, and optimizing parts of the IFS application. She's currently working on porting the NEMO Ocean model to GPUs using OpenACC. And Andrew is from Belfast. He studied computing at Imperial College London. And at ECMWF, his work focuses primarily on hardware acceleration and optimization techniques. Before joining ECMWF, he worked at ARM in a similar field. So thank you so much, guys, for presenting this webinar. And now I will let you the floor and you will tell us more about optimization approaches and their impact on performance. Thank you. You can share
Very
your
much for
screen.
the introduction. Let's see if I can get this. Is that shared
Yeah,
all
we
right?
can see it. It's perfect.
Excellent. Okay, so a brief introduction. I'm going to be talking about CloudSC, which is a physics component of the IFS. The reason we're going to be looking at this is because it's quite a significant portion of it in runtime. And we're going to have a look at the motivation for automated optimization techniques, and then how we approach that. And then I'm going to do a couple of slides on easy ways. And then Lale is going to talk about NEMO, which is the ocean model of the IFS, and her work on porting it to GPUs. I was going to have a little bit of introduction about myself, but Pelagie has done that already. One fun fact that I'll put in is that I have been here at ECMWF for 3 years and 2 days. So nice milestone. So let's start off talking about what actually are CloudSC and Loki. So CloudSC, as the name implies, is a cloud microphysics parameterization scheme. It's extremely computationally expensive and therefore slow. And whenever you have to have 4 forecasts a day every 6 hours, you want to be as fast as you can because you want to have a little bit of leeway. And once you get to the point that you're fast enough, you can increase your resolution. So it's a desirable thing for us to optimize. CloudSC is actually quite small. It's only 2,800 lines of Fortran, compared to the IFS is about 6 million odd. And despite this, it can be between 5 to 10% of the total runtime of the IFS. And I've got a very rudimentary diagram of the IFS. I would be very bold to say this or to show this diagram to some of the other scientists, but it just gives a brief overview and shows you where CloudSC lives. And as you can see, I've expanded the design of CloudSC here. It's basically just a kernel that's been extracted from the IFS. We have a driver loop, and we like to look at it because it represents other physics schemes very well. So then, what is Loki? Well, first off, Loki is a bit faceless. It doesn't have a logo. So that's why I've got that to the right-hand side. So if you've got anything that you'd like to suggest, please do so at the end. Marvel characters don't count because we can't get the copyright. But Loki is a source-to-source translation tool. It's developed in-house by ECMWF. It's originally intended for the GPU 2024 project, which is porting different aspects of the IFS to GPU. As I mentioned, there's about 6 million lines of Fortran in the IFS. So anything done by hand is it's not really going to happen. So that's why people started looking into these automated tools. However, it's not been used in the way that we're going to talk about it today, where we look at CPU-based optimizations. It was more just used for a pipeline of you start with CPU-based code and you transform it to be GPU-based code. So a lot of effort has gone into refactoring Loki so that it can do these kind of CPU-based transformations. And thankfully, it's written in Python, so it's a little bit easier to work with than Fortran. So let's get into the motivation of this. Like, why do we care about Loki? So for the previous deliverable in EUPEX, for us, deliverable 3.2, we had a poor realization of maximum performance of the platforms. You can see here, so this is a slide I've taken from a previous presentation. We were only achieving 6% of the max theoretical flops, which is, quite poor. And we're only getting 50% of the SIMD utilization on the A64FX processors, which was one of the previous EUPEX SDVs. And the question becomes, how do we make it better for the RIA processor? And that becomes quite tricky, especially as we don't have RIA processors yet. So the idea was that we would use Loki as an automated tool, and we would develop recipes for Loki so that we could put effort into that. So something that we do have, and then apply them and iterate on them once we have the actual silicon in our hands. So the question then becomes, why do we go for Loki? Like, why don't we just go for another tool? And one of the major reasons is that it's developed by us. It's our tool. We can tailor it to our code bases. I've brought up again the diagram of the IFS, and you can see I have this groupings of all the physics schemes. And that's because they generally follow the same patterns. So any effort that we invest here on CloudSC with Loki, we can reuse elsewhere on the IFS. So we get a really good use out of our time that we invest into it. And with Loki, we can make more assumptions than the compiler can. So we know how our code is structured. We know how the physics schemes are. So we can sort of give a bit of that human intuition to Loki to optimize these schemes. And we also get some insights. So naturally, you want to design your code so that it's flexible. So for us, that means that we can run over different grid sizes. We can use different blocking factors. So these are variables that we have in the code, but they're known variables. So we know them just ahead of time. Like it may not be known at compile time necessarily for all cases, but we know that if we're going to run a forecast, we're going to have a 9 kilometer grid, and that's fixed, for instance. We can also give directives to Loki. So just like you would with pragmas in a compiler, Loki supports that. So we can give real, explicit insights to Loki through these hints. And Loki is also working at a source code level, so that we don't have to rely on new compilers. So for the Rio 1 chip, it doesn't matter what compiler suite it's using, it doesn't matter what state it's in, because we just don't work at that level. We're above it with the source code. So I've talked a lot about the why, and now I'll show you the what. So this is Loki in action. It is a very contrived case, but it's just showing that if you look at these loops, it can unroll them, no bother. Even though that we're using loop A's counter in loop B, it's completely fine. It can then apply a constant propagation to this source file, and then simplify it even further. And as well, with this use case, I've manually said that S is 0 for my accumulator. But I don't necessarily need to do that. Again, you can see I've got these pragmas in place, like this Loki loop unroll. So I could tell it, treat this S to be a 0. And we can use this a lot for our code. It was designed for vector machines way back when, such as the Cray one. And that means that a lot of our code is sort of structured around blocking factors for these vector sizes. So this kind of hint that we can say, hey, this blocking size, which is called M-proma for us, it's this. You don't need to guess. And while this is all very trivial here in these slides, you can get a lot of complexity by combining these Lego bricks together. And these sort of small incremental changes can do, really fantastic things. We've just come back from the HPC workshop that ECMWF hosted, and one of our colleagues was showing that they now have a pipeline to go from Fortran to CUDA. It's about 15 transformations long, but you can put them together and it just works. It's really quite fantastic. So what recipes have we now got for deliverable 3.3? So we've got 3 main ones. We have loop unrolling now. It was only 150 lines of code, not too bad to implement. Constant propagation is a bit more complicated at 1,500 lines of code. And really the effort is not invested in writing the transformation as such. It's more on the testing. So there's 18 test cases at the minute, but that only covers, say, maybe about a third of what needs to be done. But of course, whenever you're doing this sort of automated testing on very large or automated optimization on these large code bases, testing really is extremely important. The amount of edge cases that you can do is just unbelievable. So you can't skimp on it. But this constant propagation recipe You can have it so that either it actually applies the transformation, like we saw on the previous slide, or it can do an analysis mode where it leaves the source code intact, but the actual structure of the abstract syntax tree, once it's interpreted code, it'll attach information to that. So it won't touch the actual code itself, but it'll say for the next transformation in the pipeline, you have this information about it, do what you wish. We also have the ability, as you saw on the last slide, to fold constants. However, if you're a bit nervous about your floating point operations, you don't want to disturb the accuracy on those, you can leave them untouched and it'll only touch integers. And you can either have using the loop unrolling to explicitly unroll the loops, or if you have really long loops, whether that be in code size or iterations, you can have a basic static analysis so that you don't have these loops exploding on you. And we also have definitions const prop. This one's a little bit cheating. Basically, for Fortran, you can't declare variables on the fly. You have to do it as one solid monolithic block at the start of your program. And for Loki, it kind of looks at this block and the actual code is like different sections. So definitions const prop will apply the constant propagation to this definition section. So now that I've talked about all of the setup, we get to the results. So on the right-hand side, I sort of have like the family tree of optimizations that I've attempted. And unfortunately, you can see that I have a branch starting with O2, and O2 just didn't work and needed a bit more refinement. So that's why it doesn't appear here. But the others are from this family tree. And I want to say before talking about the results that anything on CloudSC is an achievement. And I'm not just saying that because I only got about 10% performance increase. It's because this code is 50 years old and it has had, a lot of great minds thrown at it in those 50 years. So we're really kind of at the edge of what you can get out of this code. So anything is good. So we start off with the base Novec. So this is literally CloudSC as you pull it. I have vectorization, auto vectorization by the compiler disabled. And then we go on to O1. I've used that as the base of my measurements because it feels like cheating to go with Novec. Compilers these days are pretty good at vectorizing on their own. Then we go to the first transformation applied, which is the constant propagation. I was quite surprised. I actually didn't really get much out of this. Really just a flutter on the readings. But not to be deterred, I actually created the constant propagation for the definition section from the kind of lackluster results from this. And this did give me the win I was looking for, at least a little bit. Now that the compiler knows exactly the size of all its arrays, we are able to squeeze that little bit of performance out, 10%. And I want to stress again that this is a good sort of outcome for CloudSC, but also it's a good outcome for all the physics schemes. It's not just this 10% of 10% of the IFS runtime. It's 10% of all the physics schemes because Loki is able to just automatically apply it to all these millions of lines of code. So it's quite a nice result to see that you get this for free. So that's the end of my section on automated optimization. Now I'm going to take a brief moment to talk about sort of the co-design element that we've done within EUPEX, and that's through ECWays. And in particular, HPCW, which is a benchmark suite of Center of Excellence programs that are targeting different aspects of HPC systems. And the idea is to have these be benchmarks for these specific things so that we can then go back to the hardware developers and give them feedback and co-design with them so that we get a product that it's not just fast, but it's fast where it counts. We can really get an ideal chip out of this. And we're involved in this because we have some of our dwarfs, as we call them, from the IFS, of which CloudSC is one of them. And we have synchronization meetings with Evidan every couple of weeks to kind of, update the state of where we are and, what we're looking for from the hardware and the compiler stacks and what they're looking for from us in terms of benchmarks and information. And you can have a look at these benchmarks. They're just open source. And we've already had a bit of use in this. So a couple of cases, another dwarf called EC-Trans was tested over a range of ARM CPUs and compiler suites. And that's represented on the graph on the right-hand side. And you can see that some of the bars are missing. Sometimes it's only green. We've got like one blue there. And sometimes it's because the compilers just don't work with our code. And we're able to then give feedback to the compiler developers and have them iterate and co-design on their compilers. And then we can have these codes running on Exascale systems as soon as they're released. So that's all from me now. So I'm going to continue sharing and control the slide deck, but your speaker will now be Lale.
Okay, thank you. As I already introduced, I'm Lale, and like Andrew, I'm working in the HPC application team in ECMWF since August 2022. And today I'm going to talk about NEMO Ocean model and our effort to port it to GPU using manual OpenACC directives. As you might know, NEMO is an open source framework that's used for simulating ocean dynamics, sea ice, and biogeochemical process. NEMO is based on the finite difference method on tripolar grid, and it has three main components. NEMO Ocean that models ocean dynamics and thermodynamics, and NEMO Ice for modeling sea ice, and NEMO Top for modeling TESA transport. It has been developed more than 20 years old, but it can run on a CPU-only system because it's using parallel MPI-based parallel computing. NEMO is dominated by essential operation. It means that the memory bandwidth can be a key performance factor for that. So porting it to GPU can be beneficial because of the high memory throughput of GPUs that can be well suited for such a workload. NEMO is used in the operational CUBE forecast by the IFS. Currently, IFS uses a hybrid parallelization like MPI plus OpenMP with increasing more support for GPU. For NEMO version 3, 0.4 and 4, some OpenMP directives are already manually added, but increasing support for GPU also is essential because we need to meet the computing capabilities of the modern technology as well. So we focus on NEMO for ocean components, and we try to add OpenACC directives manually on NEMO for ocean components. Our primary goal is to maximize utilization by offloading more kernels of ocean components. However, we care about the performance and scalability as well. Our porting strategy to GPU is based on using on GPU and CPU macros, which allow us to keep both OpenACC and OpenMP directives, as you can see in this slide, within the code of the modules. So users are able to compile either for CPU or for GPU. Here in this slide, I put some example of on GPU macros that we use. We use on GPU ACC kernels, on GPU ACC parallel loop gang vector, as you can see in the bottom of the slide, and in the right hand side you can see how we manage the dependency for the nested loop. As you can see, we use ACC loop SIG for the most outer loop here, because there is some dependency for JK, and we just parallelize the two most inner loop here. We also, to get benefit from unified memory of Grace Hopper architecture, we also add the unified no-manage alloc compiler flag that allow us to avoid explicit memory transfer between host and device. It means that we don't need to put directive like copy in, copy out inside the code. It can be automatically done, and also it avoids the cost of managed allocation that might be done by a compiler automatically. However, we can use manage flag as well, but we prefer to use a no manage alloc currently, unified no manage alloc currently, because we can get better performance. During porting from the Insight profiling report, we realized there are some page fault inside the report. For instance, here in this slide, you can see for TRA LDF modules, we see page fault. To reduce the cost of the page fault, we also used another new class of the NVIDIA that you can see in the next slide. We use the create capture class that is new by NVIDIA, and it's allowed to pre-allocate memory on device, so there is no need for a copy from host to device, and something like prefetching happens for the temporary arrays inside the code. As you can see here, page faults are gone, and the time of TRA LDF reduced by factor 10. And here we see that the page fault can have a real impact on the performance. So we need to care about temporary arrays inside the code as well. Next slide. Yeah, so far we tried to port most of the modules of ocean components like ocean diagnostic, ocean Teresa, radar diffusion, ocean forcing, and ocean dynamics. And we also check the reproducibility of the ported module to make sure that the result we get for the ported modules on GPU are identical to CPU version. We use the ORCA-1 test case, the lower resolution test case, because currently we are in the porting stage, but porting modules belongs to vertical diffusion and testing for higher resolution like ORCA 25 and test for scalability and finding the performance bottleneck by profiling also is in progress. The next two slides also provide the performance result for comparing CPU with GPU for Grace Hopper architecture. For the ported modules, you can hear modules from thermodynamics and Teresa. That, as you can see here, the most of the modules shows better performance on GPU. However, as I already mentioned, we are in the primary testing and we just want to see first how we can reach the full coverage of porting on GPU, and then we go to performance profiling and performance comparison between CPU and GPU. As you see here, for instance, we just compared one Grace Hopper GPU to one Grace CPU with 9 threads. However, to have a more fair comparison, we need to compare the performance of one Grace Hopper GPU to one full socket Grace CPU with 72 CPUs. And for the next slide, also, I put the similar result with similar scenario and setup for porting ocean dynamics modules. That's it. And that's all from my side. Thank you for listening. If you have any question, I'll be happy to answer.
Okay. Thank you so much, Andrew and Lale, for this presentation. We were really happy to have you today. And if you have any question, you can ask directly to our experts. Please don't be shy.
Yeah, hi. A question. Loki, is something I didn't get. So does it allow for automatic instrumentation, or is it everything via API? For locking over either of you.
Sorry, I didn't quite catch the start of your question. Could you repeat it? Sorry.
Yeah, so if Loki also has an automatic instrumentation, or does it have to be to go through directives, let's say?
So you can unleash Loki on all of the source code and just say, just apply the transformation to everything. It does work. It depends on the type of optimization you want to try. Maybe you want to just unroll all loops, and that's fine. You can just let it do its thing. But I know for our code that we've got some pretty hefty loops, and we wouldn't want to do that. So you could either use directives to say just unroll this loop or exclude unrolling this loop. So it's a bit of a, it depends.
Yeah.
But yeah.
Okay, thanks.
No,
I also have a suggestion for the logo. I don't know if that will sound gross or not, but I was thinking like a centipede and a millipede, like half and half. One from CPU to GPU.
Okay, yeah. I like that. I like that. Thank you.
Thanks for the presentation.
No worries.
Other questions? No one. Okay. So if nobody has any more question, I think we can close this session. I just want to let you know, guys, that in October we have another webinar. It will be about big DFT and presented by the CEA. It's another EUPEX application. And on November, we will have SpecFM 3D by Chinika, and it's also a EUPEX application. So if you are interested, please go on the EUPEX website and subscribe to attend. Thank you again, Andrew and Lale, for your time and all the presentation. It was really interesting. And yeah, I wish you all a good day. Thank you for your attendance to this webinar. And yeah, see you. Bye.
See you. Thank you for hosting.
Thank you.
Bye.
Bye.
Thanks. Bye.